Welcome to the gases unit. It is going to be one of the easiest ones of the year, but also one of the most important because gas laws just kind of get thrown in wherever. You'll very rarely see a question that is 100% about gas laws. They're intermixed into other questions, kind of like how you saw on the stoichiometry test that we just took. So let's jump right in and get going. First thing we need to talk about are the properties. These are going to be the four quantities that are needed to define the state of the gas, and of course it's going to be the quantities that we're going to be doing calculations for. To be quite honest, the vast majority of the time we're either going to be calculating for moles or volume in a stoichiometry type problem. So first of all is the quantity of the gas, which is N, temperature of the gas, which is Kelvin temperature, always in Kelvin. I hope that I don't need to remind you, but I will just in case. 273 added to your Celsius temperature will give you Kelvin. The volume of a gas needs to be in liters if we're dealing with the ideal gas law. And then the pressure of the gas needs to be in atmospheres, again, if we're dealing with the ideal gas law. If we're dealing with one of the other basic gas laws, you can keep them in other pressures, but when we are dealing with that ideal gas law, we need to be in atmospheres. Recall that a gas will uniformly fill any container. Spreads throughout whatever container you give it, it's going to fill it up. We remember from way back in the day, probably third grade science, that gases are an indefinite volume and an indefinite shape. They are easily compressed, and they will completely diffuse and mix with other gases. Here's some stuff about pressure. You can read through that. I'm not going to read to you. Just know that pressure is force per unit area. The official unit is Newton meter squared, and which is a definition of 1 Pascal. So 1 Pascal is equal to, let's write that down. A Pascal is equal to a Newton meter squared. The barometer was something that was invented by his name was Evangelista Torricelli in 1643, and it uses the height of a column of mercury to measure the gas pressure. That's where we get millimeter of mercury. They at some point renamed the millimeter of mercury to torr, and that was to honor Torricelli, although we are usually going to see millimeters of mercury, and of course that's equal to 760 of those are equal to 1 atmosphere, which is also equal to 101.325 kilopascals. Remember, when we're talking about pressure, standard pressure is 1 atmosphere is what we're talking about, and of course standard temperature, which we'll get to later, is 0 degrees Celsius. The manometer is another device, and that is used for measuring the pressure of a container, and the gas is given by H, which is the difference in mercury levels. So there you go. So we're going to jump right in, and we're going to do one pressure conversion, and then I'm going to leave you to your merry way to figure all that out yourself. I'll show you one, and then one and done, and then you got to just know how to do it. I'm sure most of you remember this from Chem 1. So this one says 49 torr, and we want it in atmospheres and pascals. Notice it says pascals, not kilopascals. And so 49 torr, 760, 1 atmosphere, and that is 0.064 atmosphere. And then if we're doing torr to Pascal, 760 torr is 101,325 Pascal. So that comes out to 6.5 times 10 to the third Pascal. There you go. Pressure to conversions, one and done. So you're going to work exercise 2 on your own. I think you can handle it. And then that's going to take us to the beginning of the basic gas laws. And we're going to start with Boyles Law. He's known as the father of chemistry. And of course, Boyles Law, through he studied the relationships, and he found that pressure and volume are inversely proportional. Incidentally, they are the only, sorry about that, that's my fault. Forgot to say that I was going to write on it. He found that they are inversely proportional, and they are the only 2 parameters that are inversely proportional. Everything else is going to be direct. But these are inversely proportional, meaning if one goes up, the other one goes down. Okay, so let's jump right in. There's your equation, and the little graph there is just showing you the relationship, pressure and volume, and so we're going to just jump right in and do one of the equations. Okay, easy peasy. So we have Boyles Law. We're going to use P1V1 is equal to P2V2. So let's read what we have in the problem. We have a 1.53 liter sample. That's going to be your V1 at the pressure of 5.6 times 10 to the third. That's going to be P1. And then the pressure is changed, so that's definitely P2. So we are looking for the new volume. So we're going to solve for V2. So P1 V1 over P2. Because we are not dealing with the ideal gas law, we can leave our pressures in pascals, especially because they're going to cancel each other out anyway. As long as you are in the same unit, you don't necessarily have to be in atmospheres when you're doing something like Boyles Law or Gay-Lussac's. So plug that in, 5.6 times 10 to the third pascals, and 1.53 liters, divided by the new pressure of 1.5 times 10 to the fourth. So I'm going to go into this problem knowing that the pressure increased, so I expect that the volume should decrease, okay? And so when I get my answer, which I plug that in my calculator and I get 0.57 liters, I at least met my expectation. One reason that it's really good to do that is that this was our multiple choice question. You could quickly and easily throw out any of the answer choices where the volume increased. You would know those are wrong. So you could quickly throw those out, and then you could ballpark it and try to come to an answer real quick. Okay, so let's move on. Talk about ideal gases a little bit. Remember, ideal gases are at normal conditions such as standard temperature and pressure. Most real gases will behave like an ideal gas. Many, such as nitrogen, oxygen, and the noble gases, can be treated like ideal gases as well. The reason that some of those can is because they are nonpolar. And remember, nonpolar, they don't have an attraction for each other like a polar gas would. Generally, the conditions that you're looking for, and this is usually a quick and easy, I've seen it show up on several AP exams of when do they behave most ideally. You're looking for high temperature and lower pressure, and or nonpolar or very, very insignificant intermolecular forces. The reason you're looking for those conditions of high temperature and low pressure is because there's a lot of space between the particles when that's the case. The further the particles are from each other, then the most ideally the gas will behave. Okay? The further the particles are, the most ideally a gas will behave. And also, if you are looking at gases and you're asking, they're not telling you anything about the conditions they're at, but they're giving you a list, you want to look and find the nonpolar gas, and it's going to behave the most ideally. This is talking about our PV changes from atmosphere to atmosphere, so you can see that they are good at a relative low pressures, and the reason that CO2 deviates the most from ideal behavior is it has more electrons. This is going to become something that becomes more important when we get to our bonding unit, and I will talk about this extensively, but the larger the molecule is, the more electrons it has. We call that being polarizable, which is a new word for y'all. But basically that means for London dispersion forces, the more electrons, the more dipoles are being created, so it has more attraction for each other. That will become way more important when we get to bonding, but I wanted to bring that up here so you've seen this word when we get to it again. So that's going to bring us to Charles's law, and that is going to relate volume and temperature, and they are directly proportional. As I said, the only thing that's inversely, pressure and volume. Everything else is going to be direct, and we must use Kelvin temperatures all the time. If you remember, we talked about this in Chem 1, but the reason we're using Kelvin temperatures is there are no negative numbers. Because if I were to plug negative numbers into this equation, I would have a negative volume, and that is not possible. So the original law is written like this, but we go ahead and cross-multiply to make life easier. You'll never put a T2 with a V2 or a T1 with a V1. They will always be opposite. And we'll find the same with pressure when we get to Gay-Lussac's law. So, of course, formula, so I will work a problem. So very quickly, let's label our stuff. We have a sample of gas at 15 degrees Celsius. Immediately put that into Kelvin so that you don't accidentally plug it in, and has a volume of 2.58 liters. What volume will occupy this gas at 38 degrees Celsius? So immediately let's put that. This was T1, T2 is 311 Kelvin. All right. Notice that the pressure stays the same because Charles's law is good at constant pressure. So V1 T2 equal to V2 T1, and then we're going to solve for V2, V1 T2 over T1. Again, before we plug anything in, we're going to say, okay, what did our temperature do? It increased. So I expect my volume to also increase. Again, if there was a multiple choice question, I could go throw out anything in which the volume decreased and say those are not it. So 2.58 liters times our T2, which was 311 Kelvin, divided by our T1, which was 288 Kelvin. And when I throw that in the calculator, I got 2.79 liters. Okay, I feel like this is a good place to stop for this video, and we'll pick up with the next video.